Hey guys, this is video 10.3. We're going to be talking about Dalton's law of partial pressure today, also Graham's law. So I want you to add this in here. I forgot to add that to the note packet, but we're also going to talk about that. So two quick laws. This is going to kind of end the basic gas laws, and then you guys will get to do some mixed practice before your basic gas laws quiz, and then you guys can move on to the advanced ones. But like you've seen, it's all been pretty much algebra. You're solving for an unknown variable, and that's what we're going to continue doing here today. So flip to page 7 in your notes. Make sure you have a calculator, and make sure you have, it's always good to have your reference table out, just so that you know what's going on, okay? So Dalton's law of partial pressure. So this is the same Dalton who came up with the atomic theory. Those 5 points we talked about way back in like unit 2. What he said was that the pressure of each gas in a mixture is called the partial pressure of that gas. Okay, so to get the total pressure, then you just add up, or it's the sum of all the partial pressures. So, guys, that's pretty simple. You just add up, whether you have 3 gases like we have here, or you have 15, you just add them all up to give you the total. So what we can then do is we can either say, okay, if I'm given the total pressure, I could then, and I'm given the pressure for gas 1 and the pressure for gas 3, I could easily find the pressure for gas 2. All I would have to do is subtract out gas 1's pressure and gas 3's pressure from the total to then get my missing piece. So kind of that same theme like we've seen in the note videos so far, is that you're just solving for an unknown variable. So the biggest, most important thing is just be organized. Write down the variables, label them, so that you know what you have and then what you're looking for, and it makes it a little bit easier. So that's kind of the sum aspect, where you can just add them all up. We're not going to do a practice with that together on the video because that's pretty straightforward. But we're going to talk about a special case, which we'll actually use in lab toward the end of the week, before break, or when we get back from break, and that's where we actually collect gas using water displacement. Okay, so diagram, guys, it would just look something like this, where we have water, and we have a tube in that water kind of upside down, and then it's full of water. So we would bubble gas in through like a hose, and the bubbles would go up to the top, and it would start displacing and pushing that out, and we could then figure out what volume of the water was displaced. Okay, now within that we still have the same thing. The total pressure is just the sum of all of them. Now in that special case, the total pressure is just going to be the pressure of the atmosphere. So don't let that confuse you. Notice that we have subscripts here, guys. Again, that's just to help you figure out which substance is which pressure is which. So the subscript means total, or ATM is just the atmospheric pressure. PG right here is just the gas. We would actually label it, let's say, something like PCO2, okay, or P of oxygen gas. We're just going to be specific to kind of let us know and keep track of everything. The one piece here, if we're using water displacement, is the water itself in this apparatus exerts a pressure, because remember, we've talked about in the last unit how water is always evaporating. It's at the surface of the substance or of your liquid, and then those molecules are just escaping and becoming a gas. So we have some other gas besides just the gas we're bubbling into the system. It's the gas from the water. Now again, we're going to do a lab where you guys are actually going to calculate the mass of the liquid, the fuel that's in a lighter, and we're going to use water displacement method for that, okay? But this is the process we would use. Now, the atmosphere is going to have to be given, or you're either going to get from a lab calculation, like when we do the lab itself, but on a test or a quiz, it's going to be given to you. The water vapor pressure, though, it would be from a table. This would also have to be given to you. Unless you were given the pressure of the gas and the atmospheric, then you could solve for it. But it's going to have to be given to you. So there is a table that you can look up. Excuse me, but on a test or quiz, we're going to give it to you, and that's what I've done here in these examples. So let's do these two examples together. So oxygen is collected by water displacement. The barometric, guys, barometric pressure just means atmosphere. Remember, we use a barometer to measure atmospheric pressure, and temperature are such. So what's the partial pressure? So we're looking for the partial pressure of oxygen. We're given the atmospheric pressure equals 84.5 kPa. Now, the temperature here would just be what we would use to figure out this. Okay, we would just use this temperature to figure out what the pressure of the water vapor would be at that temperature. But like I said, I'm giving that to you because I'm not going to make you memorize, or you don't need to memorize an entire table that's with temperature of water and what pressure it is at that temperature. So that's where we use this temperature piece right here, is just for getting the pressure of the water. So our pressure of the H2O equals 2.3 kPa. So now we can just solve for our partial pressure of oxygen. So PATM equals, that's the total, so it's the sum of all my different parts. So the parts I have are oxygen, which is what I'm looking for, and the partial pressure of the water vapor. So if I'm looking for oxygen, I want to get that by itself. So again, like I've said with all the videos that I'm doing, I'm solving for my unknown variable first, then I'm going to plug in my numbers. So I'm going to subtract out PH2O since it's addition. Those are gone here. So now my new formula is the partial pressure of oxygen equals the atmospheric pressure minus the pressure of the water vapor, and then I can just plug things in. 84.5 kPa minus 2.3 kPa. My final answer that I'm going to get is about 82 kPa if we wanted to go to sig figs. But again, you don't have to. So if you put down 81.5, guys, that's going to be the same. Okay? So, or I'm sorry, 81.2. Okay? So, no, I can't do math today. It's 82.2, excuse me. So if you wanted to round to correct sig figs, 82 or just be 82.2. Pretty simple. Again, writing down your variables and seeing what you need to get to, that's going to help you out a whole lot. So I would encourage you guys, pause this video right now, try this problem on your own, then come back for the key. All right, so same type of problem, gas collected over water, atmospheric pressure. So PATM equals 101.1 kPa at 50 degrees Celsius. Again, that is just going to help us figure out what the water vapor pressure would be at that temperature, which again is given to you here. That's going to be 12.3 kPa. So we're looking for the partial pressure. Now, here we're not told what gas it is. It just says a gas. So we can just generally call it P sub G. Okay, that's just letting us know that, hey, that's just the gas we're looking for. So PATM equals the partial pressure of that gas plus the partial pressure of the water vapor. I need to get water vapor by itself, so I'm going to subtract it out. So the partial pressure of my gas equals the atmospheric pressure minus the pressure of the water vapor. Pretty straightforward. So that's 101.1 kPa minus 12.3 kPa. Our final answer for the partial pressure of the gas is going to be 88.8 kPa. All right, pretty straightforward. So by writing down what you have, that's going to help guide you to that formula. Now, guys, this is not a formula that is given to you, so it's something just to be aware of. But again, if you remember that partial pressure is the sum of all the individual gases, that's pretty straightforward and easy from there. Now, Graham's law is talking about dealing with effusion and diffusion. You guys should know what those mean. Remember, effusion is passing through a tiny hole. Diffusion is just the spreading out or mixing of gases. Now, the big thing you got to remember here is that the rate of effusion and diffusion varies inversely. And this should make sense to us. Inversely with the mass of the gas. So what that means is the heavier gas is going to be slower. The lighter gas is going to be higher, inversely, right? So greater mass, slower speed, and vice versa. Lower the mass, faster the speed. And that's what we're looking at here, guys. We're just looking at a ratio, okay? Notice this is the square root, so you've got to make sure that you remember to take the square root of it. So really, just to remember, it's the rate of gas A over gas B, and then you flip their masses over here, because it's the inverse. So here we go. Compare the rates of effusion of hydrogen and oxygen at STP. So we've got hydrogen and we've got oxygen. So we need to know their masses. Note, this is something that people are going to forget, okay, because it's been a little while. But hydrogen and oxygen, they are part of, Brinkelhoff. If you do not remember to account for Brinkelhoff, meaning those diatomics, your masses are going to be off, and then your final answer will be off. So keep that in mind as you're going through these problems. Hydrogen, since it's 2, there's 2 atoms, so 2 times 1.008, you would have a mass of about 2 for that. Oxygen is 16 times 2, so that's 32. So we were comparing oxygen to hydrogen, so I'm going to say my rate of H2 to my rate of O2 equals the square root of the mass of gas B. So I said that oxygen was B, hydrogen is A, so that means it's going to be 32 divided by 2. Okay, so that's going to give us a square root of 16, or a little bit less than that if you actually go out to it. So this is going to be about 4 times. Now, there's no unit here, guys, because the mass numbers would cancel out. So what you've got to remember here is that what this is saying is it's 4 times. So rate of gas A is 4 times as fast as the rate of gas B. So in our case, this is saying that hydrogen is 4 times faster than oxygen. And that's going to be your final answer. It's kind of writing that statement. Whatever you said gas A was is going to be that many times faster than oxygen. So one thing to know is, let's say you got something that was less than 1. So you got a decimal. Guys, a decimal just means that it's smaller, or I'm sorry, that it's slower. So if we flipped this and said oxygen was gas A and hydrogen was gas B, our answer would be like 0.25. Well, that should make sense, that oxygen is 0.25 times faster than hydrogen, meaning that it's actually slower than it. Okay? If you're confused with what I just said, raise your hand, call me over, I can explain it in person. Right now, pause the video, go ahead and compare the rates of effusion of fluorine and chlorine. All right, so since fluorine was given to me first, I'm going to say that's my gas A, F2. Its mass is going to be about 38, because again, multiplying it by 2 because it's diatomic. Chlorine is going to have a mass of 70.9. So I'm going to say the rate of fluorine to the rate of chlorine will be the square root of 70.9 divided by 38. When you do that, you should get an answer of about 1.37. And so again, final answer, I would say F2 is, or effuses, 1.37 times faster than chlorine. All right? So if you have questions, raise your hand. Lots of practice. Now, after you've completed all 3 of these videos, guys, now you should be good to go and do practice 2, because it's all the gas laws that we've talked about so far mixed together. Okay? Until next time, I'll see you later.